So thanks for the introduction. It's a pleasure to be here today, so thanks also for the invitation. Yes, let me introduce myself. I'm Francisco. I am finishing my postdoc right now, jointly with the Columbia University and the University of Cambridge. I have a Marie Curie Fellowship, and we'll be moving to DeepMind very soon, in October. So today we'll be talking about variational inference, which is one of the topics where I've spent quite some time during my postdoc. And so let's jump directly into it. So I have this slide kind of to introduce the notation, but also to set up the problem and the model formulation. So I will be talking throughout the entire talk about models, probabilistic models, where we have a data set, X, and some latent variables that are C. And I want you to think about this structure here, to think about it in a general way. Like, for example, if you are developing a probabilistic model of text, like a topic model, then your X is the text, and the C could be, for example, the topics themselves, the topic proportions, etc. Or if this is a recommendation system, then the X's are the ratings that the user provide, and the C could be the latent user preferences or the latent item attributes, for example. Or, for example, this could be more abstract, and this could be a variational autoencoder, and the C be the latent code, and the X your image, for example. And in that case, this model factorizes in a particular form. But in all of these examples, we can express all the assumptions about the data generating process in the form of a probability distribution. And this probability distribution is a joint distribution, P of X, C, that's at the top, which generally factorizes as the likelihood times the prior, or that's pretty general. And in all of these problems, we are interested in finding the posterior distribution. The posterior distribution is the distribution over the latent variables once we observe the data, once we have access to the data. So we condition on X. Of course, I do not need to mention that this posterior, for most models of interest, it is intractable. And it is intractable because it involves an intractable integral here in the denominator. But nevertheless, you are interested in finding this posterior because this allows you to explore the data or make predictions. For example, if you want to make predictions on future data points, you need what's called the predictive distribution that involves the posterior. So you need this object. Or if you want to explore the data, for example, learn something about what are the topics that are present in your document collection, or what are the preferences of a particular user of a recommender system, then you also need the posterior in order to just explore these variables. The central goal, as you may know, the central goal of Bayesian inference is to approximate this posterior. So this is the general topic of the distribution. How can we approximate this posterior? And you know that there are many ways to approximate a posterior distribution. One of them is MCMC. You have had a very interesting lecture this morning about it. The other classical way to approximate a posterior distribution is variational inference. You have also had several lectures about variational inference, so I could skip these slides, but just to set up and make sure that we're all on the same page, let's just recap a little bit. Let's review variational inference for just a couple of minutes. So again, our goal is to approximate a posterior distribution. We will do that by defining a simple family of distributions that we denote by Q. So this Q here is something that you posit, so it's your approximating distribution. For example, you can choose it to be a Gaussian or any form that you like. Anything in general that's simple to work with. This distribution has some parameters theta. In the case of if you choose a Gaussian, then theta is the mean and the covariance of the Gaussian. And variational inference, what it does is to fit these parameters theta in such a way that the, say, Gaussian approximation becomes a good approximation of your posterior distribution, becomes as close as possible to the posterior. We measure this closeness in terms of KL divergence. So to formalize that mathematically, you would find the theta that minimizes the KL between your approximation, your variational distribution Q, and the posterior, which is the object that you're interested in. So variational inference recasts the Bayesian inference problem into an optimization problem. I always like to show this diagram, which you have also seen before, but anyways, this ellipse here, well, sorry, this is like the space of all possible distributions over the latent variable. In this space, there's the posterior that resides somewhere. It is a distribution over the latent variables. Is it the mic? Yes. And this ellipse here represents all the distributions that we can, all the family of parametric distributions parameterized by this parameter theta. So for example, the family of all Gaussian distributions. And within this family of distributions, we would like to find that distribution which is closest to the posterior in terms of KL divergence. And to do that, well, there are several different ways to do that, but the most common one is that you initialize your variational parameters somehow randomly so you start in a point in that space, and then you run your optimization method, which typically involves computing gradients and following those gradients until you hopefully approach the optimal solution. In general, well, not in general, but in many cases, these gradients will be stochastic, and you're doing stochastic optimization, and that's fine. Okay, so with that in mind, we know, oops, I forgot to mention that we are minimizing KL divergence between our approximation and the posterior, but I said at the beginning that the posterior is what we want to approximate. We don't know the posterior, which means that our objective function, the function that we are minimizing, is intractable also, because the posterior is intractable. But fortunately, the trick of variational inference is that minimizing the KL is equivalent to maximizing what's called the elbow, evidence lower bound, which takes this form, and that's represented over there. And that form does not involve the posterior. That's good. In fact, this is an expectation under Q of the log joint minus log Q, where, again, Q is the approximation. And the log joint, in general, is a nicer object than the posterior, or at least it's something that we can generally evaluate or even take gradients with respect with. OK, so we have the variational objective function, and we want to maximize this with respect to theta. In classical variational inference, and in fact, I say classical, but it is still widely applied, is mean field variational inference. In mean field variational inference, you assume that your approximating distribution Q factorizes as a product over individual latent variables. So you would have a product over Q of Zn, and each of these Q distributions has its own variational parameter, its own, say, mean and variance, theta n. This leads to simple algorithms that are fast, are useful in many cases, but sometimes they are not accurate enough. Like, for example, it is well known that if you have a posterior distribution like this one, the mean field variational inference tends to underestimate the posterior variances. And that's because of the form of the mean field approximation. It is also because of the form of the objective function, which is an inclusive KL divergence. So this lecture is about expanding the variational family. So can we work with some other variational family that's not mean field, that doesn't have this nice factorization, in order to expand the expressivity of the variational distribution. So if we had this picture before, where this ellipse here is the family of distributions that we can form by tuning the variational parameters, then we would like to expand this family of distributions so that hopefully it includes the posterior of interest. In practice, that might not be the case, but at least it might be closer to the posterior of interest. So we would like to expand the variational family, and we will do that using, well, there are many ways to do that, okay? So there are many, many ways to do that. And here you have like a bunch of references. One way to do that, perhaps one of the first attempts to go beyond the mean-field family was structured variational inference, but there are also many other methods that try precisely to do that, to find more expressive variational families that provide better approximations to the posterior. Like, for example, mixtures, sampling mechanisms, spectral methods, linear response estimates. In particular, linear response estimates is something that you do after you have fitted a mean-field variational distribution. There are copulas. Well, you had also a lecture, I believe it was yesterday, about normalizing flows, also, which is an invertible transformation. There are also hierarchical models, implicit distributions, semi-implicit distributions, and in fact, the frontiers among all these different methods is not even clear. Some methods that I have put within an item in this list perhaps can also be interpreted as corresponding to another category as well. So there are many ways to expand this variational family. And I'm not going to defend any of these methods. I'm not going to claim that any of them is the best and just choose this one always, because there's no like a clear winner here. But I will restrict the attention in this presentation to implicit distribution and semi-implicit distribution. So which is in this class of methods, I will go to that one. So again, we want to expand the variational family Q using implicit distributions. That's what we will focus on. So what's an implicit distribution first? So, well, you've probably seen implicit distributions already during the summer school, but also before. I will use this definition of implicit distributions, where implicit distributions are those that are easy to sample from, so you can produce samples from the distribution quite easily, but they have an intractable density. Because it is intractable, I put it in red always, because we cannot compute or evaluate that density. And of course, when we have a distribution defined this way, the natural question or the main issue is how do we solve an optimization problem which depends on an intractable object. So remember we were solving this, we were maximizing this elbow, which is expectation under Q of the log joint minus log Q. But now we just declared that the approximating family Q is implicit, which means that it has an intractable density. And therefore, this objective becomes intractable. We cannot even estimate with samples. We cannot evaluate this objective, mainly because of this log Q term that appears here. Although also Q appears here, but we will see that's not a huge issue. Okay. So before we see how to solve this problem, I want to make sure that everyone understands the goal that we have. Again, we want more expressive variational distribution. And in this example here, I have 3 different targets in orange. And the blue dots that we have on top are samples from our variational distribution, from Q, are samples from Q. So as I said before, when we have an implicit distribution, we cannot evaluate the density, but we can sample from it. So in all these cases, the samples from our variational distribution are a good fit to the targets that we want to approximate. Even though we cannot evaluate Q, we can still proceed and we can sample from Q as a proxy to samples from the posterior. So this is our goal, to tune the parameters. There will be some parameters of the variational distribution Q. So we want to tune these parameters in such a way that the samples that we produce match the posterior. I will divide the lecture in 3 parts. All of them are about implicit distributions. Even with implicit distributions, there are many different methods that we can use. So I will start with the one that's called adversarial training or prior contrastive estimation, which is perhaps arguably one of the first methods to use an implicit distribution defined by a neural network. So let's jump into that. So I've been saying that we want to use an implicit distribution, and an implicit distribution is a distribution where we can sample from, but we cannot evaluate the density. But how can we form such a distribution? Well, here's one way. This picture here is my attempt to draw a neural network. So we have imagine that you have a neural network where theta are the weights and biases of the neural network. And now the input is a random variable. So if the input is random, then the output C will also be random, just because the input is random. So if you follow this process of generating noise at the input and passing the noise through a neural network with parameters theta, then the output will be also a random variable distributed according to some probability distribution. It's just that the output of the neural network. So we can use this neural network, this model as our variational distribution in such a way that the samples that we have at the output approximate the samples of the posterior. So this is an implicit distribution because, well, you can see that very easily. It is easy to draw samples from it. You just sample some noise at the input, and then you just compute, do the forward propagation through the neural network and compute C as a function of the input. So it's very easy to produce samples from this scheme. However, you cannot evaluate the density Q, right? There's no way you can evaluate the distribution at the output because this is not a normalizing flow, so it's not invertible, so you cannot compute that. However, the distribution that we have, the distribution Q, will be very flexible because, well, we have a non-linear mapping in between the noise input and the output. So in principle, the distribution of the output can be arbitrarily flexible. And what we want to do is to tune theta, tune the weights and biases of the neural network in such a way that the distribution of the output approximates the posterior. Is everything clear? OK, so I didn't say that, but please interrupt me with questions whenever you have one. I prefer to be interrupted rather than to have all the questions at the end. So whenever you have a question, just raise your hands at any point. OK. So why is, I've been saying that using implicit distributions in variational inference is hard because, well, we now have an objective that depends on Q. We cannot evaluate Q. So why exactly is it hard to use a distribution like defined that way in variational inference? What's the main issue here? Well, recall the elbow again, expectation under Q of log join minus log Q. This elbow has two terms, although it can be written in different ways. This is the one I will use for now. This elbow has two terms. So one of them is the model contribution, the log joint, and the other one is the entropy. So it's, well, the entropy appears once you take the expectation, right? So you have the model term plus the entropy term. Now, if we are solving an optimization problem, then we need access to the gradients of this objective with respect to the variational parameters, correct? So these gradients will be intractable in general, and that's true even if you don't have implicit distributions. However, in many cases, you can at least estimate these gradients using Monte Carlo. So let's see if we can do the same thing here. So I compute here the gradient of the objective, which is, and rewrite it as an expectation of something else, right? So this expectation now is taken with respect to the input noise. This is what's called the reparametrization trick that you're probably familiar with already. But in case you aren't, the main idea here is that to compute the gradient of the objective, I can just express it as an expectation of the input noise and then evaluate something else. So if you achieve that, then you just need samples from this distribution Q of epsilon, evaluate whatever is inside, and that gives you an estimate of the gradient, an unbiased estimate of the gradient. OK, so that's generally what's done with reparametrization. However, in this case, when we have implicit distributions, this log Q term that appears here is in red, and that's intentional. This is intractable, an intractable term. We don't have access to the density Q, right? So in these two terms, okay, sorry, I will go back. In these two terms, just focus on this equation here. This is the gradient of the objective that has two terms, right? So the modal component, I have the same equation here. This is, again, the gradient of the objective. So now, for the modal component, as I said, you can very easily produce a Monte Carlo approximation just by sampling. So this is an expectation under Q of a gradient. And then what you do is just draw samples from Q of epsilon. And again, like Q of epsilon has no parameters. This is a simple Gaussian, like a standard Gaussian or something like that. And then so you can sample from here, and then average what's inside the argument of the expectation, and that gives you an unbiased estimate of the modal component. Very easy. All you need is to take gradients of the model, of the log joint. But that's, let's say, that's something that you can do, well, using AutoDiff or anything like that. Now, for the second component, for the entropy term, you have the gradient of log Q. And as I said, this is where the issue arises. Why? Well, if you derive this gradient and you just do the math, you can apply the chain rule. It is gradient of log Q with respect to the argument times the gradient of the neural network, times the gradient of the function inside. And then because Q itself depends on theta, then you will have another term, but that cancels out. That is 0 in expectation. So the point here is that you get this, just the first part, like gradient log Q. Now, if you want to approximate this gradient using Monte Carlo estimates, as we did before for the model component, it turns out that you need log Q, but you also need you not only need log Q, you also need gradient of log Q with respect to its argument. And that gradient is not available. It's not available because, well, Q itself is intractable. So the gradient is also intractable. So that's why doing a variational inference with implicit distributions is complicated. And let's see one of the ways in which you can get rid of that problem and still solve the optimization and maximize the elbow. Okay, so let's go back to the objective, which is the elbow. As I said, maximizing the elbow is the same as minimizing the KL. And the elbow has, as I said, two components, the model component and the entropy component. There's another alternative expression for the elbow, which maybe you have also seen before, probably so, which is log likelihood minus KL to prior. So we can rewrite this objective. First of all, the model is the log joint is the log likelihood plus the log prior, right? So you can rewrite the model component, just take the likelihood component, the log likelihood component. And then the prior that comes from the joint, the prior you put it together with the entropy component. And essentially you get the expectation of the log likelihood minus the KL between Q and the prior. It's just one line to go from one to the other. So, and if you want to see that explicitly, the KL is just expectation under Q of log Q divided by P. So this is, again, I haven't done anything here. All I've done to go from here to the equation at the bottom is just a little bit of algebra. Just rearrange the terms that appear in the objective. But it's the same exact objective. Okay, so why do we want to express it in this way? Well, we will apply something that's called density ratio estimation, and we will see how density ratio estimation can help us solve the optimization problem. So the main idea of density ratio estimation is to use this expression of the objective as expected log likelihood minus KL to prior. So using this expression of the objective and approximate the density ratio log Q divided by P. So the first term here is not intractable. It is the same, by the same reasons that I explained before. You can use reparametrization to estimate the gradient. And the issue arises from this term alone. So if you're able to approximate the log density ratio here, then maybe there's hope and you can take gradients with respect to theta, which is our goal here. Okay. So this is the main idea of density ratio estimation, so let's go into it. Again, I like to repeat the equation so that everything is clear. What's above is the objective that we want to maximize. And now let's imagine for a moment that we have labeled samples from Q and P. And we assign, say, class 1, class y equals 1, to when the sample comes from the distribution Q, and class y equals 0 when the sample comes from the distribution P, from the prior, from P of C. Now, if you observe C alone, and I ask you what is the class, assuming that both classes are equally likely a priori, then what's your answer? Well, you can think about it, or you can read it there. The optimal classifier is given by Q divided Q plus P. So that's the optimal classifier for a given point C. So if I give you a value and I ask you which distribution did it come from, then you would evaluate this and you give me the probability of the sample coming from class 1, from class equal, from Q in this case. Okay. So there is an expression for the optimal classifier that I call D star. And again, this D star is the probability of class 1. And we have defined class 1 as the sample coming from Q. Okay. So once we have that, then it turns out that you can express the density ratio, that's the main problem that we have in the objective, this density ratio here. You can express it as a function of the optimal classifier. And, well, to see that, just look that 1 minus d in here at the bottom. This 1 minus d term is just, if d is this guy here, then 1 minus d is just p divided by the sum. So once you take the difference of the logs, all you're left with is q divided by p, because the term q plus p, the denominator, it cancels out. Okay, so this is promising. We have found a way to get rid of this intractable Q distribution that we have in the objective and replace it with something else, which is, in this case, a classifier. Okay, so again, this is what we have done. We write the density ratio as a function of the classifier. Now, if we have that, then we would this is a theoretical result. This is assuming that we have access to an optimal classifier D star. In practice, we don't have access to this optimal classifier because the optimal classifier, again, is Q divided Q plus P. And, well, we cannot compute it, right? But we can train a network, an auxiliary network, to distinguish between samples from Q and samples from P, from the prior. And which is exactly what the classifier is doing. The classifier tries to distinguish between samples from Q and samples from P. Okay, so if we want to achieve that objective, then it turns out that this optimal classifier, we can obtain it by maximizing this objective here. So by maximizing the expected value of a discriminator under Q, plus the expected value of log 1 minus classifier where the expectation is taken with respect to the prior. So if you maximize that and you let the classifier be freeform, be anything, then you obtain the optimal one. Of course, in practice, you cannot let it be freeform, and then you would use an auxiliary network to parameterize this discriminator. So you would train D using a neural network that distinguishes between samples from both distributions. But imagine you do that. Imagine you do that, and imagine that that the discriminator that you find is very close to the optimal one. Then you could rewrite the elbow as we had before as the expected log likelihood, and then here I have replaced the density ratio that we had before with the expression from the top of the slide. So I have replaced the density ratio with the difference between log D and log 1 minus D. Okay. So this is where we are. So now if you want to actually run the algorithm, if you want to run variational inference, what should you do, given all of these equations? Well, the algorithm is not so complicated. This is the objective again, just to remind you, but the algorithm would be, you will repeat 2 steps. You will repeat this, iterate between these 2 steps. So one of the steps, you follow gradient estimates of this objective with respect to theta, using the reparametrization trick that I mentioned earlier in one of the slides before. And then once you follow a gradient, compute a gradient estimate and take a gradient step with respect to theta, then you feed the optimal classifier. You train a classifier D that hopefully approaches the optimal value. And then repeat. Well, here you can already see one of the limitations of this method, which is that, well, the second step. For each theta, for each value of the variational parameters during the optimization process, I have to feed a classifier. And feeding a classifier implies, well, running quite some number of iterations until it converges. So this procedure will be, well, it's likely to be slow. So in fact, that's one of the limitations of density ratio estimation, which is that the discriminator D needs to be trained to optimum after each update of theta for these equations to be true, to hold. In practice, that optimization method is just truncated to a few iterations of the discriminator. So you just run, say, for example, 10 iterations of 10 steps to optimize the discriminator for each step of the variational parameters. Another limitation of density ratio estimation is that it might lead to unstable training, especially at the beginning of the optimization when the discriminator, if the discriminator doesn't catch up quickly. That's another. In fact, this algorithm doesn't necessarily converge. And one of the reasons is that it might, the discriminator might not be catching up, and then the optimization process just becomes unstable. And one of the main issues is when you have high-dimensional C, high-dimensional latent variables. In that case, the discriminator typically overfits. And when that happens, it gives values that are either 0 or 1. It's clearly not giving you a good frontier for classification between samples from P and samples from Q. So in general, I would say that one of the main limitations of density ratio estimation is when you have a high-dimensional setting. Because in general, like doing this trick that we just mentioned is a nice approach, but in high dimensions, you may encounter several issues. Okay, so how can we deal with that? Although we have, this was like density ratio estimation was the first method that I wanted to explain here about how we can proceed when we have implicit distributions. But as I said, it suffers from several limitations, and in fact, there has been several alternatives in the literature to try to avoid that. One of them is what's called kernel-based density ratio estimation. UIVI, I don't know how to pronounce that. Well, the K is for kernel, for sure, and VI is for variational inference. And there are also another class of methods which are semi-implicit distributions. There are a few papers on that, and in fact, that's where I will focus next. So I just want to very quickly mention that the other paper, the kernel-based density ratio estimation, is actually a very cool trick. You can have a look at the paper. I like it, but I don't have time to cover it. So I will just jump to the other class of methods. Okay, so that leads me to the second part of the talk, which is about semi-implicit distributions. Are there any questions so far? Yes.
Could you, on slide 20,
24? Oh. Yeah, I would say this should be an approximation, right? Because the way, the motivation for that is that if you have the optimal classifier, then the log ratio can be expressed in this way. Do you see that? Or okay. So if that's true, then you can replace log q divided by p with this term here at the top. And that's exactly. So of course, like that's only true for the optimal classifier. This is an approximation, assuming that you have trained that your discriminator is flexible enough, and assuming that you have trained it to optimum, then you can make this approximation. Any other question? No? Yeah. Of C, the latent variables, yes. And yeah. So just so that it gets recorded, the question was about when I said here that the discriminator overfits in high dimensions, I meant high dimensionality of the latent variable space. So high dimensionality of C, of the latent variable C, because the discriminator takes C as an input. This is trying to distinguish between samples that came from Q and samples that came from the prior. Okay, if there are no more questions, then I will jump to the second part of the talk. Okay, semi-implicit distributions. So let's recap a little bit. I've been talking all about using this structure at the top as to define an implicit distribution, and then using that distribution in variational inference, right? And we have said, we have also stated before that, when we have the objective written in this form, like the model plus entropy component, the problem, the issue that we find is that the entropy component is intractable. And in particular, we found out in a previous slide, we needed the gradients of log Q with respect to C, with respect to the input. And that's where the issue arises, right? Like we cannot compute this gradient here to estimate the gradient of the objective. Okay, so semi-implicit distributions are trying to find a way to compute the entropy component. Okay, so instead of estimating the ratio, P divided by Q, or Q divided by P, we are trying to directly estimate somehow this entropy component, the second term. So we will go back to the expression where the model component is expressed as a log joint. Okay, so semi-implicit distributions want to avoid this density ratio estimation, so to hopefully work in larger dimensional settings, in higher dimensional settings. There are, within semi-implicit distributions, there are different methods. There is one method that lower bounds the elbow. That's called UIVI or CV, semi-implicit variational inference. And then there's another method that tries to estimate the gradients using sampling, which is unbiased implicit variational inference. So both of them, I will explain both of them, but both of them have something similar, which is that they use a semi-implicit construction of Q. So let's explain first what's a semi-implicit construction. Okay, it's very simple. Now, imagine that you have the scheme before where we had some input, a neural network, and some output. And now the output is random because the input is random, because we input some random noise there. Okay, so a semi-implicit distribution is indeed, this block here at the bottom looks similar, right? This block here. This is just, well, I'll do that with the pointer, with the mouse. So this block here is the same block as above. So we have some input, we have a neural network, and we have some output, right? But now think of the output. Do not think of the output as the latent variable C as before. Instead, think of the output as the parameters of a distribution. For example, I input some noise, I push it through the neural network, and what I obtain is the mean and the variance of a Gaussian. And now I sample from that Gaussian, and I obtain Z. So this second step, which I mentioned, just sample from a Gaussian, is a conditional distribution, Q of Z given epsilon, because if I know epsilon, then I know the mean and the variance of the Gaussian, and this is just this Q here, this conditional is just a Gaussian. Okay, so this is what's called a semi-implicit distribution. In particular, what we typically do is to choose something that's simple, for example, a Gaussian conditional Q of Z given epsilon. And this Q of Z given epsilon, for example, this is what I described before. If it is a Gaussian, then it is a Gaussian whose mean and covariance are both functions of epsilon, the input, random input, and these functions are parameterized by the neural network parameters. Okay. So even though I have declared we have built this distribution using Gaussians, like everything that's random here, like this conditional, we have said, okay, this is Gaussian, and the prior of epsilon at the bottom, on the left, we said, okay, it can be any simple distribution, like a standard Gaussian also. So even if both distributions are Gaussian, the overall distribution is very flexible, because it can be rewritten as an integral of Q of epsilon times the Gaussian conditionals. Now, this integral cannot be solved, but it can be seen as an infinite mixture of Gaussians, where there is a nonlinear transformation between the input here and the parameters of the conditional. Yes.
A question to the semi-implicit distribution construction. So I have a question to the semi-implicit distribution construction. So what's this age of theta?
Yes, I haven't explained that yet. Yes, okay. So there are some, this is my bad. So there is some notation here that I haven't explained yet, H and U. For now, I just want to think of it about as the decoder of a variational autoencoder. So you have some random noise, you push it through a neural network, and that gives you the parameters of a Gaussian. Just that. Yeah. Okay. Well, my point is that once you sample from that Gaussian, from that Gaussian conditional, whatever is at the output is not Gaussian distributed, because there is a nonlinear transformation here, right? We have a neural network in between. Okay, but this distribution is still, although we call it semi-implicit, still implicit. And it is implicit because, well, it has these two properties that we mentioned earlier. It is easy to sample. Just sample the input, obtain the mean and covariance of the Gaussian, and then sample the output Z from that Gaussian, okay? So it is very simple to sample from, but we cannot compute the density. And that's why I put it in red still. We cannot compute the density because we cannot solve this integral here. Okay, any other question with this construction? Okay, so we will assume, I've been saying all the time that this conditional is Gaussian, and in fact, I've saying that because we assume that it is a simple distribution that we can easily work with. And in fact, we assume that the conditional, not the full Q of Z, which is intractable, but the conditional Q of Z given epsilon is reparametrizable, and we also assume that it has a tractable gradient. And note that assuming that it has a tractable gradient is not the same as assuming that we have the gradient of log Q, which is the one that we need to solve the variational problem. So we haven't solved the problem yet, okay? This is still intractable. So all we have is the gradient of our conditional distribution. Now, I have been saying Gaussian because the Gaussian meets both assumptions. It is reparametrizable, and I believe this answers your question before. It is reparametrizable in terms of an auxiliary variable U, and that follows a standard Gaussian. And then we can obtain the output as a deterministic transformation of both u and epsilon. So to put it in another way, if you want to sample from this semi-implicit distribution, one option to do that is sample epsilon, then push it through the neural network, and then sample from the Gaussian with those parameters. Another way to sample from it is the same, sample the input noise, obtain the parameters of the Gaussian, but then sample an auxiliary random variable u that follows a standard Gaussian, and then obtain the output as a deterministic transformation of both u and epsilon. This is all the notation that was missing from the previous slides. So all my point here is that we can reparameterize the conditional. Also, the conditional needs to have a tractable gradient. And in particular, if you write, the Gaussian also has this property. I mean, the particular form of the gradient is not important. What's important is that the gradient of a log Gaussian is something that is tractable. And we can evaluate. OK. So with that in mind, with that construction in mind, I mentioned earlier that there are two methods. One that's called semi-implicit variational inference, and the other one that's called unbiased implicit variational inference. I will explain both, but somehow briefly. So for this first one, semi-implicit variational inference, the main idea is to find a lower bound of the elbow. So the elbow is the objective of variational inference. So instead, it finds a bound, and then maximize the bound. Now, the bound is given here. It looks like it's a little bit ugly and long, and it is. But, well, I can give you a very brief, I will not show why this is a bound. If you have questions, yes, you should ask Dimitri. But I will just very briefly mention that, just to give the intuition, that this part here, in the big parentheses, is just an average of Q of C given epsilon. An average with respect, so I will do that with mouse. This part here is an average of the conditional in green, right? And if you take the average of the conditional in green with respect to samples epsilon, which are different, then this approximates Q of C. And if the whole line at the bottom approximates log Q of C, then what you are left is log model minus log Q, which is the elbow. So that's like the intuition, but it turns out that besides this intuition, this is also a bound on the elbow. And in fact, this bound has a parameter L, which is how many components you use here to approximate QC, right, or log QC. Of course, the larger value that you choose here, the better. But the main point is that now this lower bound does not depend on the intractable Q anymore. There's no red in this bound, right? It's just all green. And because it is all green, then we can take gradients of that bound, maximize that with respect to theta, and that's exactly what semi-implicit variational inference does. Just maximizing this objective with respect to theta. So I have the bound here again. As I said, the free parameter L that you have here, it controls the tightness of the bound. So if it is very large, it can be shown that as it grows and grows and it approaches infinity, then the lower bound approaches the exact elbow, which is a nice property to have. The reason, again, is that if L is really large, then this summation here of conditionals becomes an integral, right? And then you're summing an infinite number of them. Then it's the same as doing the integral with respect to epsilon. Yes? Or taking the example, yeah.
Hi, thanks for the talk. In the original paper, in the CV paper, they said that this sum works as a kind of regularization.
Yes.
Could you go into that? Because I didn't understand when I read the paper.
Yeah, so they derive this bound following a set of steps, right? We first derive another objective, then they add a regularization, because they say that otherwise the network degenerates. So I wouldn't need the paper in front of me, but essentially the main idea is that the first objective that they derive, if you optimize it without this added regularization, then what happens is that the network here degenerates. By degenerates means that no matter the input, you will get the same output. So the epsilon is ignored, and essentially, if that happens, then your whole distribution Q is just a Gaussian. It's equal to the conditional. Yeah, so then you have that degeneracy issue. So then they add another term, and then they say, okay, that's the motivation that they give, and then they say, okay, let's optimize this new objective instead. That's what they do. But I think that I know that when they derived this paper, they didn't know that this objective is a bound on the elbow. That came afterwards by the work of people in the group. Yeah. So I think that's why they do that in several steps, and they say, okay, now let's add a regularizer, and they are trying to be very. And they also, in fact, they also derive an upper bound. Yeah, there's more information in the paper. Yeah. Okay. So as I was saying, this bound now depends on a free parameter L that the user chooses, right? You choose this parameter L. The larger, the better. But also, well, if you choose a very large value, this converges to the elbow, which is a nice property to have. Another nice property of semi-implicit variational inference is that it allows for a semi-implicit construction of the prior in variational autoencoders. But I will not go into that. So that's all about the semi-implicit variational inference method. Now let's go to the unbiased implicit variational inference. And I apologize for all methods having so similar names. So in this case, we are still using a semi-implicit construction. Okay. So we are in the same setting where we have a distribution Q that's defined with this two-step process. And we are still with trying to solve the same issue, which is that this gradient log Q is intractable. We still want to avoid density estimation, but the main difference of unbiased implicit variational inference is that it attempts to optimize the elbow directly, instead of optimizing a bound like the previous method does. So how can we do that? Well, the key idea of this method is to rewrite the gradient of the entropy component, so gradient log Q, which is the object that's intractable, as an expectation of a function that we can evaluate. So if we achieve that, if we rewrite this gradient as an expectation, then you can simply draw samples from whatever this distribution is, evaluate the function inside, and that gives you an unbiased estimate of the gradient that we needed, right? So that's the key idea here. So how do we do that? Well, it turns out, well, I will not show the proof here unless someone is interested. It's not so complicated. It turns out that the gradient that we want, the gradient of log Q, which is the one that we want, is equal as the gradient of the tractable component in expectation. So that's very powerful because it means that if we are able to draw from this distribution in blue, then we can estimate the intractable gradient that we want by just computing the gradient of the tractable conditional. So the trick is to rewrite the intractable gradient as the gradient of the distribution in green. Okay, so as I said, I skipped the proof for this. If anyone is interested, please feel free to ask. And all what's left is to describe how to draw samples from this distribution in blue, which I am intentionally omitting for now. So let's first assume that we can sample from the distribution in blue. Let's assume we can do that. So how would the algorithm proceed? So okay. So if you want to optimize the L1 and estimate the gradient, the algorithm is not so complicated. First, you draw samples. First, if you want to use reparameterization, you just draw samples from both epsilon and u, which are the sources of noise, the only two sources of noise that we have. In fact, they are generally standard Gaussians. Yes, I will go into that later. Yes, this is, okay, I will go into that now. So the algorithm just draws these two variables, epsilon and u, then computes the output as a deterministic function of both, because we are using reparameterization. Then once we have epsilon, u, and c, we have everything. We can compute gradients. We can evaluate the gradient of the model, the gradient of the transformation that we have in between. with respect to theta, which we need to then plug in the gradient estimator. But then we sample a variable that I call epsilon prime from this distribution in blue that I haven't just described how to sample from it. And then we approximate the interactable gradient that comes from this term just with the gradient of the conditional evaluated at epsilon prime, where epsilon prime is the sample from step 4. So the algorithm is just these 5 steps. It's not complicated. And all that's left is how to sample from the distribution in blue, right? So the distribution in blue, we call it the reverse conditional. And we call it the reverse conditional because it is a distribution over the input noise given the output C. Normally, I have defined the conditional earlier as the probability distribution over C over the output given epsilon. This is exactly the opposite. This is Q of epsilon given Z. Now, how could we obtain samples from this distribution in blue? Well, one option to obtain samples is to apply HMC, Hamiltonian Monte Carlo, or in general some sampler. And the target distribution, we can compute up to a proportionality constant because the reverse conditional is proportional to the simple distribution on epsilon times the direct conditional. And the direct conditional, again, is a Gaussian. We can compute it. So what this means is that we can evaluate the reverse conditional up to a proportionality constant, as usual. But HMC is slow, right? If we need the samples within an algorithm, within a variational inference algorithm, and if we need to apply HMC at each step of this variational inference algorithm, then the whole thing will be slow. So how can we accelerate this? So recall the algorithm again. The first thing that we did in the algorithm that I described earlier is to sample the sources of noise, right, which are standard Gaussians. And then I computed C as a function of the 2 inputs, epsilon and U, and in particular as a function of epsilon. What this means is that we already have samples, epsilon, comma C, that come from some joint distribution, which we have sampled as epsilon coming from the prior and then C coming from this Gaussian. But we could have factorized this joint the other way, like Q of C, which is a marginal distribution that we cannot compute, and the reverse conditional in blue. So the point of this line here is to show that or to imply that the sample epsilon that we have already is a sample from the reverse conditional. So we already have one at this point. However, the algorithm, unbiased implicit variational inference, needs the sample from the distribution in blue to be independent, in principle, from the sample epsilon that actually generated C. And of course, if we just set epsilon equals epsilon prime, then we don't have that independence. So what we do is to still apply HMC, but initialize at the epsilon that we sampled before. By doing that, we initialize the sampler at stationarity, and any subsequent sample will still be a sample from the reverse conditional. So that's exactly what we do, and in fact, we just ran a few iterations of the HMC steps, HMC steps, and it worked. It worked well. So this is just summarizing what I just said. So we initialize the HMC at the stationarity with a sample from epsilon, and then any subsequent iteration will reduce the correlation between both the initialization and the sample that we actually use. So this is exactly how I obtained this plot that I showed at the beginning of the presentation, where we are approximating 3 different targets. And in this case, the distribution Q is a semi-implicit distribution, and I've been using this unbiased implicit variational inference method. So I've also applied this unbiased implicit variational inference method on other models, like, for example, this is a multinomial logistic regression, which is essentially a multi-class classifier, a multi-class linear classifier. And I believe, yes, I have 2 data sets, and I am comparing in these plots the performance of semi-implicit variational inference and unbiased implicit variational inference Both are kind of more or less the same. Perhaps unbiased implicit variational inference is a little bit better in terms of both the elbow that we obtain, which is at the top, and the predictive log likelihood, which is at the bottom. And this is another comparison of both methods in a variational autoencoder setting. So in the case of the variational autoencoder, we want to find at the same time the model parameters and the variational parameters. So we want to do inference and learning. I think you're all already familiar with that. And for that, we use an amortized distribution Q, which is semi-implicit. What this means is that this Q is intractable now. And in fact, it involves an integral of a tractable component and a tractable prior. But this tractable component has a neural network between epsilon and the parameters of the Gaussian. So we applied this method on the VAE and found that it has better predictive log likelihood. So the numbers in this table are log likelihood on the test set. Okay, so yeah, I think it's time to start part 3.
Could you quickly comment on the variance of the gradients that we computed? Because then throughout the summer school, we have been told that, okay, a lot of these... Can you quickly comment on the variance of the gradients that we compute? So we have been computing the gradient of log densities, which throughout the summer school, we have been told like might have high variance. And in this case, we don't even know what the functional form of the density looks like, right? So in practice, do they have like high variance? Or can you just give a brief comment if you don't have any?
That's a good question, yeah. So the question, yes, if I can say something about the variance of the gradients. I cannot say much. So all the gradients that we are using here are reparameterization gradients, and we know that these have smaller variance than the score function gradients. That's something that we keep even with this method. I am not sure how the variance of, for example, the gradients of these two methods compare within each other, but even further, they're not even optimizing the same exact objective, because one is optimizing a lower bound, and the other one is targeting at least the elbow. So you would have gradients of different functions, and I'm not sure if it's fair to actually compare them. So yeah, that's all I can say. Yeah. Okay. So yes, the last part of the presentation, which is okay. It's also I'm also going to define an implicit distribution, but in a different way, using MCMC. And is there another question? Oh yes, sorry.
Yeah. So my question is like comparing the two methods on semi-implicit variational inference and unbiased one. So in the semi-implicit case, if we increase the value of L, we should get an unbiased estimate of elbow, right?
Yes.
And in case of unbiased UIVI, the problem is you have to run a HMC chain to get a sample from the reverse conditional, right?
Yes.
So computationally, which one is more efficient?
Yes, that's also a good question. Like how do we, of course, like the computational complexity of each method depends on its own parameters.
Yeah, right,
so
right,
how do you establish a fair comparison?
Right,
So what we did in the paper is to set up, so choose, like I remember, some value for the semi-implicit variational inference and value for the bound, and then choose a value of the number of MCMC steps in such a way that we do the same number of evaluations of the conditional. So that they have, so let's say, fix the computational complexity. And for us, that for the unbiased implicit variational inference method, that means a small number of MCMC iterations. Sorry, HMC iterations, because each iteration involves leapfrog steps and has to evaluate the conditional multiple times. So we took that into account to do the same number of evaluations in both. Yeah. Okay. Okay, so as I was saying, this is the last part of the presentation. Where I will also define an implicit distribution, but in this case, instead of using a neural network, I will use MCMC. So if you, for some reason, haven't quite followed all the details of the previous part, you can still this is a good point to pay attention again and continue with the presentation. You will be able to follow it. So our goal is the same as before. We want to expand the family of variational distributions. And to do that, we will start from an explicit variational distribution Q. So this explicit, what we call, when I say explicit, I put it in green, meaning that we can compute the density. And this variational distribution is, for example, your mean field approximation or anything, any tractable variational distribution Q that you want to use. Now, the main idea is to start an MCMC chain initialized with a sample from this distribution. So to do that, we will sample C node from this implicit distribution and then apply some MCMC sampler for a few number of iterations, say T iterations, where T is a parameter again, something. For example, 10 MCMC iterations. The sampler targets the posterior P of sigma x. So the longer the chain is, the closer we get to the posterior. But the main idea of this method is to tune the variational parameters theta in such a way that the initialization is a good initialization for the sampler that comes afterwards. That's the main idea. So if that's the case, then you need a few number of MCMC steps. So this is still an implicit distribution under the definition that I gave earlier, because we can sample from it. And in fact, the sampling process is just written above, just sample an initial C node and then apply a sampler. But we cannot evaluate the density. We cannot evaluate the density, well, because there's an integral here, and in this integral we cannot evaluate the transition, the T-step transition kernel of the target, of the sampler. So the point is, we can sample from it, we cannot evaluate the density, as is usual in this lecture. So again, how do we do maximization of the elbow when we have something that's intractable, right? The log Q term that appears here, again, the entropy component is intractable. So that's the first challenge that I wanted to mention. But in this case, we also have another more subtle challenge, which is that we might find optimization issues because the objective might depend weakly on theta. This is not always the case, but we don't have control over it. Meaning that, imagine that you initialize, as I said, you have an initial distribution and then you run a short MCMC chain. You don't really know if the MCMC chain has converged or not. If in general, maybe it hasn't, if the number of steps is small. But if it has converged, if it is close to the posterior, then what it means is that the final distribution Q that you obtain is actually similar to the posterior. And if it's similar to the posterior, it means that it has forgotten the initialization, the initial point. And if it has forgotten the initial point, it means that it doesn't depend on theta, which are the variational parameters. In short, what this means is that if that's the case, if the chain is too long for any reason, then your Q converges to the posterior, and the posterior doesn't depend on any parameters, and then this objective doesn't depend on any variational parameters at all. So that's a potential issue here, but of course the main one is that the objective is intractable. Okay, so in this work, what we try to do is to find an objective distribution that avoids these two challenges. We will call that objective variational contrastive divergence, VCD. And for it to be a valid divergence, well, we will require these two properties. First, it has to be non-negative for any value of the variational parameters. And second, it should become 0 only when the initial distribution is already equal to the posterior. If you have these two properties, then it makes sense to minimize such an objective, right? Because at the optimum, then you recover the posterior. Okay, so that's exactly our goal. To find such an objective, and again, like we are starting from the elbow, and we want to replace the elbow with an alternative objective that doesn't suffer from these two challenges. Now, to find that objective, we first note that when we run MCMC, the distribution that we have becomes closer to the posterior, becomes closer to the posterior in terms of KL divergence. In fact, the KL between the MCMC improved distribution Q and the posterior is smaller than the KL between the initialization and the posterior. Well, we know that if we let the MCMC run for infinity, for a large number of steps, it will converge to the posterior asymptotically. But this inequality is true even if we run only one MCMC step, or only 2, or only 10, whatever, any number. This is always true. And in fact, this is a strict inequality. This is a strict inequality that becomes equality only when the initialization is at the optimum, at the posterior. If the initialization is at the optimum, then both KLs are 0, which is because the initialization cannot be further improved, right? Okay, so one way, so starting from this inequality here, we take everything to the right-hand side and say, okay, let's take the difference between both KLs, the KL of the tractable component minus the KL of the implicit component. And that's an objective that we could have. That objective is a divergence, actually, because it is non-negative. It is non-negative, well, we just declared that above. And second, it becomes 0 only when you're at the optimum. That's the only case where this difference becomes exactly 0. So this is a proper divergence that we could minimize with respect to the variational parameters, except that we can minimize it because it is still intractable. Okay? And the reason why it is still intractable is that there is a log Q hidden in the second KL, in the same way as with a standard elbow, where we have a log Q also that is the source of all our issues. So to remove that intractable term, we add a regularizer. So we take the difference that we had before and add another KL between the improved distribution and the initial one. Now, even with this regularizer, the whole objective that this is what I call variational contrastive divergence. So this is the objective that we were trying to find. The whole objective is still a divergence. And the reason is that, well, the first term was already non-negative. We saw that in the previous slide. And the second term is a KL, so the whole thing is non-negative. And the only way for this to become 0 is when the initial distribution is equal to the optimum, to the posterior, to the P of C given X, in which case both terms are exactly 0. And that explains why this is still a proper divergence that we can minimize. But what's more important, okay, so this is a divergence. We like this objective. But what's more important is that this is now tractable. And it turns out that the intractable log Q term that we had before from the second KL cancels out from another log Q term that appears in the third KL because they have different signs. So there's no longer a log Q term in red in this objective. But it also addresses the other challenge that we mentioned earlier about the weak dependence. Just to recap a little bit, the second challenge was that if your MCMC has converged, then the objective doesn't depend on the variational parameters. That doesn't happen here. Why? Because if you let the MCMC chain to converge, then Q equals the posterior, the Q in red equals the posterior, so this term here cancels out. And the third term, well, this Q here will be exactly the posterior. So what you recover is a symmetrized KL divergence between the initial Q and the posterior. So even if your Markov chain has converged, this still guarantees dependence between the objective and the variational parameters. Okay, so here you will have to believe me. It turns out that if I take the three KLs that we had before that define our objective, you can rearrange the terms a little bit. It's just algebra. And you get to this expression at the top that has 2 expectations. It's the same objective, the same exact thing, except that now instead of 3 KLs, I have 2 expectations, but it's the same thing. But now what this shows is that the first component there only has green. Okay, before I go into that.
You suppressed T dropped out of the contrastive divergence. So is it just that the Q theta, so Q theta is really Q theta T, right?
Well, I'm using, yes, I understand the question. Yes, it is.
Okay.
I'm using a different notation here than in the poster. That's the, so what I call QT here is just Q, just so that all the slides have the same, yeah.
Okay, thank you.
Yeah, but thanks. Okay, so I was saying that this is the same objective as before, the sum of the three KLs, and it has two terms, two expectations of the same quantity. That's interesting. Now, the first expectation here is the negative standard elbow, right? So if you look into this looks like the elbow, log joint minus log Q, and expectation with respect to Q. So this is the elbow with respect to the initial distribution Q node. Now, the second expectation is an expectation of the same quantity, but taken with respect to the improved distribution after MCMC. What this means, once you have these two terms, is that you can use any techniques to estimate the gradient of the first component, because the first component is a negative standard elbow. And there are many methods in variational inference to estimate the gradient of that in order to, well, in this case, minimize the objective. So you can use reparameterization or scan function gradients. In the paper, we use reparameterization. Now, for the second component, which is the new part, it turns out that you can also express the gradient of this expectation, as an expectation over functions that you can evaluate. And again, I don't have time to go through the details. What's important here is that you can form Monte Carlo estimates of the gradient of this objective. This is what you should take from this slide. Okay, so once we know that we can take Monte Carlo estimates of the gradient of the objective, then the algorithm to minimize this objective is so simple. You just sample from your Q node distribution, then you run T MCMC steps to obtain a sample from the improved distribution. Then you estimate the gradients. We just mentioned in the previous slide that you can do that, and then take a gradient step with respect to the variational parameters. And then, yes? A question over here? Yeah, and just repeating these steps is exactly the algorithm that we apply.
Is there an intuition behind the second term in the objective function?
Yes. Good question. So when I define this objective, first of all, the kind of the intuition behind the entire objective is what some people call the principle of minimum improvement, which says that if your initialization is very close to the target, then after you run MCMC, the distribution that you obtain marginally is very similar to the initial one. So this whole objective is trying to reduce the discrepancy between both. That's the intuition. Now, the first term here is actually trying to do that. This is a form of discrepancy between the initial and the final one, as expressed as a difference of chaos. But this term here is also a discrepancy between the final and the initial one. So that's more or less the intuition behind it. Yeah. I mean, each of them separately would be a valid objective. But if you consider each separately, it's intractable. So it's only when you combine them both when you can run maximization, well, minimization. Okay, so, okay, I have some more time. So here I have a set of toy experiments where we are trying to approximate 4 different targets. And these targets are the distributions in orange. And I don't know if you can clearly see the slides, but okay. So within here, there are some circles in blue. Okay, here, also here as well. So these circles in blue are the approximations that you obtain if you apply standard variational inference, like minimizing the standard KL, so, yeah, or the standard KL of variational inference. Now, if instead of that you minimize what we call the variational contrastive divergence, then the initial distribution Q node is represented in green. So this is the tractable component of the approximation that I have defined. Now, why is this? What is the story behind this plot? What this is telling us? What this is telling us is that the distribution that you obtain, the initial distribution Q node, which you obtain if you minimize the variational contrastive divergence, has higher variance than the distribution that you obtain if you just optimize the elbow. And the reason for that is that we know that we have said before that the variational contrastive divergence converges asymptotically to a symmetrized KL divergence between the initial distribution Q node and the posterior. Now, here we can already see that effect. Like we know that the elbow in variational inference tends to underestimate the posterior variances. Here we have higher variances, higher variance approximations. Of course, you could say that this is asymptotic convergence, so we should not expect to see that in the picture. Well, this picture was obtained with only 2 MCMC steps, and you can already see that increased variance effect. Of course, this is only a 2-dimensional target, so maybe in higher dimensional settings you need more iterations. But I found it interesting that even with such a number of MCMC steps, you can already achieve distributions with higher variance. We also ran experiments on latent variable models, where, again, you try to optimize at the same time the model parameters and the variational parameters. And in this case, the model involves a product of our individual data points. So we use amortization, where the variational distribution that we use depends on X explicitly through the initialization. So this initialization here, this Q node, is parameterized by a neural network that takes X as input and returns the mean and the variance of a distribution over C node. Okay, so we ran experiments on 2 models that factorize in this way. One of them is logistic matrix factorization. Is this just a matrix factorization model with Bernoulli likelihoods? And the other one is the variational autoencoder. It's in the other table. For each method, we have 2 different data sets and 3 methods. We compare 3 different methods. So the numbers in the table are, again, predictive log likelihood. And if you optimize the variational contrastive divergence, you obtain at least as good performance as the other method of Hoffman et al. 2070, and much better performance than if you use just standard variational inference. The reason for that is that this method leads to better approximations of the posterior, which in turn leads to better models. So this is the last slide, just a quick summary of everything I have been talking about. So the goal of this talk was to expand the flexibility of the variational distributions that we use, going beyond the mean field approximation. We have seen several methods to use implicit distributions within this framework. One of them is density ratio estimation. The other one are semi-implicit distributions, and we have seen 2 methods for that. And the third one, the third part of the talk, was about refining the variational distribution using a few MCMC steps. These methods that I have presented, especially the semi-implicit and biased implicit, the semi-implicit distributions and the last one as well, I have found them to be stable. I haven't had any issues with training as it might happen with density ratio estimation. And they also gave good empirical results on probabilistic models, but also on the probabilistic models like the variational autoencoder. With that, I would like to conclude. So thanks for your attention. And if there are more questions, I'll be happy to answer. Any question?
Hi, thanks for the lecture. As far as I saw, this work is pretty recent.
Yes.
So I'd like to ask you if you have any further plans on expanding on that?
one of the things that we would like to do, well, there's several things, but for example, one of them that I'm now thinking about that is that with the last part of the talk, the one with MCMC, we have one of the gradients, I skipped that part, but one of the gradients, if you derive the expression of the gradients, this term here, when you estimate that, it might have high variance, that gradient. And we are using control variates to mitigate that. But it would be nice to form a reparameterization estimator of that term instead of a score function estimator. That's something that requires to reparameterize through the HMC, which is not straightforward, and that's one of the things that we're currently thinking about.
Yeah. Hey, so you use this complicated approximations for the posterior, but in the end, the form of your posterior is still dependent on the prior that you choose, right? And you never really mentioned what kind of prior do you choose for all of that?
So repeat the question again. Is there any?
So what I don't understand, or what I would like to know apart, is that apart from the posterior that you choose to approximate in this fancy manner with neural networks and the semi-implicit algorithms, how do you parameterize, or what kind of prior do you choose, right? Yeah. Because in the end, your KL divergence still depend on the form of the prior, and if your prior is simple, then I guess no matter how fancy the posterior, it's not going to learn that much.
Yeah, so I'm assuming through the entire presentation that the model is fixed. So there's an exception, and we'll go into that later, but the model is given. Someone hands you the model. For example, the model might be latent display allocation, or the model might be multi-class classifier with certain, so the prior and the likelihood are both specified. So someone hands you that, and then you just do inference on targeting that posterior. Now, it's true that some of the experiments that we run, we also want to do maximal likelihood over certain parameters. For example, parameters of the likelihood or parameters of the prior, if there are any. In this case, I'm not doing that. I'm just maximizing with respect to the parameters that go here into the likelihood term. But there could be parameters of the prior that you could also maximize with respect to. Yeah, that's not in the experiments. I'm assuming that the model is fixed and then doing inference on that model. Yeah, thanks.